Section 6.1 is slope fields and Euler's method. So, differential equations, all functions y that satisfy dy dx equals 3x squared plus cos x. So we're looking for all the possible solutions to this equation. We're solving for y. We're going to get any antiderivative, which can be a function of the form y equals x cubed, the antiderivative of 3x squared, plus sine x plus c. If you remember, this is called our general solution. Okay, so that's the general solution of the differential equation. If the general solution to a first-order differential equation is continuous, the only additional information we need to find a unique solution is the value of the function at a single point, called an initial condition. A differential equation with an initial condition is called an initial value problem, and it has a unique solution called the particular solution. So we have general solutions with our plus c, and then particular solutions with an initial condition. So here's an example. Find the particular solution to this differential, dy dx equals e to the 2x minus 3x, whose graph passes through the point 1, 1/2. This is our initial condition. So the general solution, the antiderivative of this function with our plus c, our general solution, applying the initial condition, substituting 1/2 for y, and substituting 1 for my x values, I can then solve for c. C is this expression, and if I tack that on to the end of my general solution, I get my particular solution. Okay, so general solutions and particular solutions of differential equations. Okay, so here's another one. This time, we're given f prime of x, which is cos x squared. So we're going to use the fundamental theorem to solve this initial value problem. So f of x is the integral. If we do the integral from 3 to x, then when x is 3, this becomes 0, plus 5 then gives us our value that we want for f of 3. So in other words, f of 3 would be the integral from 3 to 3 of cos t squared dt plus 5. This all is 0, so we do have our solution or our initial condition of f of 3 equals 5. So two ways to solve a differential. One using the fundamental theorem when we're given f prime, the other to use our dy dx format and solving for y. So two different methods of solving. Okay, slope fields. The differential equation gives the slope at any point. dy dx is a slope. This information can be used to draw a small piece of the linearization at that point, which approximates the solution curve that passes through that point. Repeating that process at many points yields an approximation called a slope field. So let's do an example of this as well. Construct a slope field for this differential equation. So at any point, 0y, it will be where the cos of 0 equals 1. The slope at any point where x is pi, you notice that this equation is only dependent upon the x value. So any point where x is 0, we'll get 1. Any point where x is pi, we will get negative 1. All odd multiples of pi over 2 will be 0, and the slope is 1 along any line where x is plus or minus 2 pi. So we've got a lot of choices here, but lots of things that just depend on x. So they're going to write these in one at a time. Again, putting in their pi, negative pi, plugging in when we have pi over 2 or negative pi over 2, and finally going out to 2 pi. So this is our slope field, and if we picked an initial condition, let's say when y equals 1, 0, 1, we could follow the slope field and we would get a pretty good approximation of our cosine curve. Should have really started at 0, 1, but that's okay, we get the same thing. Okay. So this is our slope field, which is another way of approximating a function. The last thing we're going to look at today is Euler's method. I don't know whether you did this last year or not, but what Euler said was, well, if I have a slope and I know a particular point, I can approximate using dy dx another point on that graph. And then if I follow the slope at that point, I can find another point on the graph. So I get all these little tiny line segments using Euler's method that approximate the curve, but every time I move from one point to the next, I do end up a little bit further off of the actual curve. Copy this down, and then let's do it a step at a time, and I think it will make more sense. So pause and copy. Okay, use Euler's method with increments of delta x equals 0.1 to approximate the value of y when x equals 1.5, given this function and this initial condition. So we're going to set up a table. So we're going to start with the initial condition of 1, 2. At that point, dy dx equals x plus 1 or 2. Plugging this value into this. We know that our delta x is 0.1, and that's going to be a constant all the way through, because that's a given. So delta y now is dy dx times delta x. So if I multiply these two together, I get my change in y. So my change in x is 0.1. I add that to my initial condition. My change in y is 0.2. That's my new ordered pair. I'm going to take that over to here and start all over again. So at this point, the slope, dy dx, is 2.1. Delta x was a given. I can find my delta y using these two values and create a new xy ordered pair. I continue the process until I get up to my 1.5, which is what I wanted to approximate, and I approximate that at f of 1.5, my value is 3.1. And again, we'll do some more of these together in class, so save any questions you have till class time.